Alright, so here we are with using Cpctc to prove parts of triangles are congruent, and we will go over what each of these letters means. So basically what happens is up until now we've used different shortcuts in order to say that triangles were congruent, and now that we've taken that shortcut we're going back to this phrase because now we're saying, well, we skipped over a few pieces, so what do we do with those? So here it is, Cpctc. It stands for corresponding, so matching, parts. So for instance, the top angle and the top angle of congruent triangles, again, that we've said are congruent. Okay, and again, that's because the shortcut misses a few sides and angles. So because the shortcut missed some angles and sides, now we can actually go back and say, hey, well, we took that shortcut, and so it turns out the rest of those angles and sides are congruent as well. So again, it's a justification and a proof after you have proven two triangles are congruent. So the problem is that people will start to say that two triangles are congruent by Cpctc, but this is actually after. So watch out for that. Remember that side, 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 side angle, side, all of these guys here are used, use corresponding parts to prove triangles congruent, and so therefore after you use one of these shortcuts, you can then use Cpctc to say that this third or last side or whatever is congruent. So, taking a look, we're going to end up using a coordinate plane proof. So this is what we're going to do a lot more in the last section of Chapter 4, but right now we're just kind of looking at this one to prove. So, we're going to use the given points to prove the angles are congruent in this. So, again, how would you do that? We're going to use side, side, side. From side, 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 we're going to use Cpctc. Hello. To then say that some angles are congruent. Okay, so taking a look at this, and it is already plotted for us here, we are going to have each of these three making up these two triangles, triangle DEF and GHI. And so what we need to do is use the distance formula, which we did practice, in order to find the length of GH so that we can match it to one of the sides in the other triangle. So we're using side, 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 and the way we're going to get the sides rather than tick marks is by actually calculating them. So for instance, triangle GHI has three sides. One of them is GH, the other is HI, and the third is IG. And then we also have the other triangle, which is DEF. And so in that triangle we have side DE, side EF, and side FD. And we need to find each of these lengths. So how would we go through and do that? Well, we're going to take each of the coordinates of those 2 points and subtract them. So to find GH, we use G, which is -2, 1, and H, which is 0, 5. So if we write those coordinates for G and H here, we can now plug them in. So this is an X and a Y, and we'll call that X1 and Y1. And this is an X and a Y, and we'll call that Y2 and X2. Taking a look at our distance formula, that means that the distance between GH is going to be the square root of x2, which is 0, minus x1, which is -2. We'll square that, and to that we'll add y2, which is 5, minus y1, which is 1. Alright, simplifying that a little bit, 0 minus -2 is going to be 2 squared. And then to that we'll take 5 minus 1, which is going to be 4 squared. And so really we have 4 plus 16 in a square root, or the square root of 20. So GH is the square root of 20. Alright, next one I'm going to do is HI. So we need the coordinates of HI. So those are 0, 5, and 1, 3. So to find the length of HI, we're going to end up with the square root of, if we apply our x's here, this is an x and a y of the first point, this is an x and a y of the second point. So we're going to end up with x2, which is 1, minus x1, which is 0. Once we subtract that, we'll square it and then add it to our y2, which is 3, minus our y1, which is 5, squared. Alright, so that means that when we simplify, we end up with the square root of 1 minus 0, which is 1 squared, plus 3 minus 5, which is negative 2 squared. And 1 squared is then going to be 1, and negative 2 squared is going to be 4. So we have the square root of 5 as HI. Alright, then the last one, we're going to do I and G. So we need the coordinates of those two. So we have an I of 1, 3 and a G of negative 2, 1, which we'll plug in. Again, these are our x and y for the first point and our x and y for the second point. If you labeled these as the second point and these as the first point, you would still get the same distance. So that hopefully makes sense, since we're going to be going from between the same 2 points, so it wouldn't change the length. So if we plug that in, we're going to do our x2 minus our x1. That difference, will then be squared, and then to it we will add the difference of our y2, which is 1, and our y1, which is 3. Alright. And so we end up with a simplification of negative 2 minus 1, so the square root of negative 3 squared. Sorry, the negative 3 squared. And then to that we'll add 1 minus 3, which is negative 2 squared, which simplifies to be the square root of 9 plus 4, or the square root of 13. And so that's IG. So what happens here, since we have 3 different lengths, and yes, you could make them into decimals, but we'll find that they'll be the same anyway, is now we're going to find one of these 3 that match with these, so that we can actually say that they are congruent. So we're going to start out with DE, and so we need the coordinates for D and the coordinates for E. So D is negative 5, and E is negative 3, negative 1. Alright, so if we want to find the length of, let's see, GH, we're going to go ahead and mark our x's as x1 and y1, this one over here as x2, y2. And so we'll end up doing the square root of x2, which is negative 3, minus x1, which is negative 5. That difference will be squared, and then we'll add the difference of y2, which is negative 1, minus y1, which is negative 5. And that difference will be squared. Alright, so we end up with the square root of negative 3 plus 5, so that's going to be negative 3 plus 5 is 2 squared. And then to that we'll add negative 1 plus 5, technically, so 4 squared. And so that's going to end up being the square root of 4 plus 16, which is the square root of 20, which hopefully we then realize is the same as GH. So I just labeled this as GH, but it's DE. Alright, so DE is this similarity. Alright, so we now know that DE and GH are the same. So I'm going to go back to this one, and from the distance formula, we know that GH and DE are congruent. Alright, then we'll move on to the next one. So the next one is going to be EF. So we need the coordinates of EF. So E is negative 3, negative 1, and F is negative 2, negative 3. So if we assign them as our x's and y's for the first point and the second point, we can then put them in for the distance of EF as the x2, which is negative 2, minus the x1, which is negative 3, squared, and then add the difference of our y2, which is negative 3, minus our x1, which is negative 3. Oh, sorry, y1. Alright, then we simplify a little bit, and we're going to get negative 2 plus 3, so 1 squared, and then negative 3 plus 1, so negative 2 squared. 1 squared is 1, negative 2 squared is 4, and so we have the square root of 5 for EF. Which again now gives us this idea that HI is going to be the same as EF, because they're both square root of 5. So now we know that HI is congruent to EF. And so we have one side, a second side, and so now we need our third side, otherwise we don't have a shortcut. So the next one is going to be the points of F to D. And so F is negative 2, negative 3, and D from before is negative 5, negative 5. If we apply that this is x1 and y1, and this is x2 and y2, we have that the distance of FD is the square root of our x2, which is negative 5, minus our x1, which is negative 2. That difference squared, and then added to, where is it, negative 5 again, minus y1, which is negative 3. Alright, so if we simplify that a little bit, we're going to end up with the square root of negative 5 plus 2, so negative 3 squared. And then we'll add negative 5 plus 3, so negative 2 squared. And so we actually have the square root of 9 plus 4. And so we get the square root of 13 again for EF. So we've now matched EF with IG. So IG and EF are going to be congruent as well. So it's FD. I just went to the previous one. Alright, and so now because we have side, side, we can then say that the triangle are congruent, and then we can say that Cpctc says that any angle within them, which they're saying DEF, so that's this one, and GHI, so that's this one, are congruent. So again, notice that we did the work to then prove by side, side, side. Then we use CPC to say, oh, that extra angle, it can be congruent now. So kind of a long proof. All right. Taking a look here, a helpful hint is to work backward when planning a proof. Generally, when I do a proof, I'll kind of go through the givens a bit, okay? But in this one, if we say, oh, we're going to prove this angle, how do we get to the angle? Well, the only thing we can do with these points is sides. So they're saying a helpful hint would be to work backwards. For instance, to show that ED is parallel to GF, we would look for a pair of angles, because we know that in order to prove that two lines are parallel, you need some angles, so you're kind of working back from the end. Then look for triangles that contain the angles, because then you can match the sides. So you can work forwards, you can work backwards, you can work from the middle, which of course doesn't help, but that's why the two-column proof idea is so helpful, because you can kind of jump around. Alright, some more proofs here. Given in this first phrase here, we have NO parallel to MP. Okay, so of course, because we have parallel lines, we are probably going to have congruent angles, most likely because of alternate interior. Because I do see this transversal, and therefore this angle and this angle are probably going to be congruent. In fact, they are. So NOM NOM is going to be the same as, so what did I say, NOM PMO. Then they also give us that N and P are the same. Alright, and so I don't really see a whole lot left except that MO is going to be congruent to MO because of reflexive. So it's not really given in here. I don't see any X's to make vertical angles, so that's kind of where we'll stop there. So taking a look at the proof, this guy is the given. Then from there we've already done NOM and PMO, and that was because of alternate interior angles. Alright, then we have MO and MO, and that's the reflexive, like we have in the previous slide. And now they're saying, oh, by the way, the triangles are congruent. So how did we get there? We had an angle, and another angle, and a side. So we're either doing angle, angle, side, or angle, side, angle. So going back, we've got an angle, and then not the side between them. Remember, this mark here does not mean that they're the same, it means they're parallel. So this is angle, angle, and then side after them. So we can say by angle, angle, side that those two triangles are the same. Then we get to say that angle NMO and POM, where's NMO? NMO and POM. So these other angles are going to be congruent. Why? Because of Cpctc. So now that we've proven triangles are congruent, that was step 1, and now step 2 is use it to then say that they're parallel. So this is going to actually be by the converse of the alternate interior angles. And remember that we don't necessarily need to write converse, but that is technically what it is. Alright, and then our last proof here, we're given, ooh, I see an X, so we'll probably have some vertical angles. But either way, J is the midpoint of KM. So I'm going to know by the definition of midpoint that KJ is congruent to JM. Oh, and then they're saying and NL, so NL is also cut in half by J. So by the definition of midpoint, we know that NJ is going to be congruent to JL. Okay. Then they want you to prove that KL is parallel to MN. Where's KL? KL. Oh, I already said it, but vertical angles is going to be within here. So I guess it doesn't really matter what triangle. What are we doing, KL? So we're definitely going to want to say that this angle and this angle are congruent, because this angle isn't really going to help us with the triangle. So we're going to want angle KJL, because it will talk about this opposite side, and that being congruent to KJL, so MJN. Notice when I was naming those, I went along the one side and then the two. So when I named the other one, I went along the side that was a one tick mark to the two. Alright, so first thing we're going to write down is the given. So the given is J is the midpoint of KM. What was the other one? KM and NL. Alright, then notice by definition of midpoint, and this is actually going to be two things, so we're going to write both of these pieces, that KJ and JM are congruent as well as the other set. And the other set is NJ and JL. Alright, then we have vertical angles, so we already talked about that, and that's going to be angle KJL. And how it matches MJN. Alright, and then we've got side angle side, and they're just kind of giving specifics here. Don't really need them, but either way. Step 2, of course, is the sides, and step 3 is the angles. So if we look at how it's set up, of course, angle side side isn't an option, but you can see that we're talking about this angle and this side, and the angle between them. So writing it, it's side, angle between them, side. So by side angle side, we now know that triangle KJL is congruent to triangle MJN. And so then Cpctc is trying to lead us to alternate interior angles. So which ones of these would make alternate interior angles in order to say that this side is parallel to this side? Well, if we're talking about this transversal, we would need this angle and this angle. It turns out if you want to identify this transversal, you could alternately be doing these two angles. So either one of those is correct. I'll just go with the one I did first, which was the yellow, red one. So we're going to do JLK. And that's going to be congruent to JNM. By Cpctc, because it's a piece of that triangle that now can be congruent as well. And so now we get to say that those two sides, KL and MN, are parallel. Yeah. And that's by the alternate interior angles, which is what we did in the previous one as well. So that was a bunch of proofs, kind of putting all of the pieces of triangle congruence together, all those shortcuts, but then now we have this like next step. Once you've proven something congruent, what can you do with it?